Okay, AP Calculus AB, Unit 5, Day 1. Okay, this unit, we're going to continue doing more derivatives. We're going to learn a lot of derivative rules, pretty much all the rest of the derivative rules, and some other new techniques for taking derivatives. So these first notes are kind of like notes for the first 2 days of assignments. The first page is probably what we would mostly do as a lesson one day in class, and then the back page would probably be a separate day. I'm going to go and just do them both for this video. Here we go. This is, even people who had taken pre-calc have probably seen some of those rules from last chapter, seen some of that stuff, limits, and at this point I think we should probably all be seeing stuff brand new. So we're going to listen. We derived the power rule last unit with the definition of the derivative. What would Newton do? Well, Isaac Newton, he would definitely do the forward secant approximation. So that's where you use the point you wanted at and point to the right of it. You can go backwards secant, left-sided. We could do symmetric, but usually we're all going to use this one. A lot of times it's very common. So we did this work last time. We used Pascal's triangle. We expanded this, and those terms cancel each other out. We factored h out of everything. And remember h squared and all the rest of it, all the other stuff in here had at least h squared. So we factor at least h squared out of all of them. Factor h out of that. That's the hole in the graph, right? And so then we reevaluated it, and that term went away to 0, and we had n x to the n minus 1. So that was the power rule, derivative, n x to the n minus 1. I wouldn't really memorize it as a formula, but more of a pattern. You multiply by the current exponent and decrease it by 1. Okay? Now, we're going to go ahead and create some other rules. Now, this is a product rule. Now, let's investigate some ideas here. Some think that maybe, if you haven't had much experience with it and you might guess, you might think, oh, well, we could just take the derivative of each part separately and then multiply them afterwards. And derivatives are very much based off limits. So you might think, well, we can do that with limits. No, cannot do that. Now, let me try and convince you, okay, with a good counterexample. So let me come up with something simple like x cubed times x squared. And let's use that approach for the derivative. Let's say, okay, well, that'd be 3x squared times 2x to the first would equal 6x to the third. Okay, well, another way we could do it, let's see what the answer should be. We could simplify that and say, well, that's x to the fifth, right? Rules of exponents. And the derivative of x to the fifth, we feel very confident, is 5x to the fourth. These should be the same, but they're not. So that just clearly shows you that that approach is not valid. So let's try and figure out what the approach is. We're going to try and drive it. Okay, now these derivations take a little bit of creativity, and I wouldn't expect you guys to figure it out but on your own, but let's see if we can follow it. I have a lot of stuff written down here. We'll add some more stuff. Okay, so here's the derivative of a product, and this would be us putting it into the definition of derivative. Plug x plus h into both of them, plug x into both of them, all over h, rise over run. Now what we're going to do is we're going to bring in some new terms. I'm going to bring in a minus 5x plus h gx. And I'm allowed to do that if I then add it back in. So sometimes we do this kind of method with like completing squares where we add new terms but then we got to counter it. So I'm just adding and subtracting the same thing. So this is okay. All right, that should be okay. That's worth it. Now I'm bringing this in to make some interesting things happen. Okay, so I'm going to bring this fx plus h out of both of these. There's a gx plus h and a gx. I'm going to let's see. Okay. All right. So fx plus h, gx plus h, gx. So I'm grouping these together, and then I'm going to group these together and take out the gx out of both of them. So I'm just factoring out a GCF. And then I'm going to use properties of limits that say I can actually do the limit of this and then limit of this separate. And then I can do the limit of all this, and I can do the limit of this and the limit of this separate and multiply afterwards. That's properties of limits that we learned last chapter. And so what you should realize is, so what we did is we break up the limits after we kind of do this grouping stuff. And this should look familiar. That's the definition of the derivative of g. And hey, here's another derivative of f, right? So we force these derivatives to kind of come out of this pattern. So then now if I plug h equals 0 into here, that's just going to be f of x. And then this is the derivative of g. And then this is just going to be gx. And this is the derivative of f. And this right here is how we take the derivative of a product. Okay? And it's called the product rule. So it is f times g prime plus g times f prime. Again, I wouldn't memorize this as a formula. It's more of a pattern. It's actually kind of hard to mess up. It doesn't matter which one you start with. You're going to take one and times it by the derivative of the other plus the other way around. You could do gf prime first and then fg prime second. Just one times the derivative of the other plus the other way around. Okay, so that's called the product rule. So order doesn't matter. It's harder to mess it up. Now the quotient rule, I'm not going to show you the derivation of it. Okay, I'm going to write it down. If you're interested, you can look in the book, and they show more derivations. We're not going to do them all. I'm going to do some of them just to kind of help you appreciate it. Okay, so the quotient rule is g f prime minus f g prime. So it seems very similar to the product rule, right? Except that there's subtraction. So now the order does matter, and it all gets divided by g squared. Okay, so that's the rule. Okay, order does matter. Okay, so this is a little easier to mess up. So there is this cute little saying, I think I showed you guys on a warm-up last unit, that I'm usually anti-cute sayings, but it works. And it's so easy to mess up. Low d high minus high d low all over low squared. I'm very careful. I usually put a lot of parentheses around all these when I actually do the work. Low d high minus high d low all over low squared. We go, if you want to be extra cute. So anyways, now some other notations are f prime dy dx, y prime, second derivative, is like this. This is a little, the reason it's the second derivative is like that is because it's the derivative of the first derivative. So it's d dx like this. So that's why the squared gets put right here on the top, and that's why the squared gets put here on the bottom. Okay, now these different notations are because two different guys were pretty much kind of figuring out calculus around the same time. The primes were Newton's notation, and the dy dx was Leibniz. And I kind of like this because it's kind of more like slope, which it is. You kind of see that change in y over change in x. You could think of the little d as like a difference in y or a difference in x. So each of these are nice for different reasons. And some of them I use more specifically for certain kinds of problems just because they're less confusing based off the kind of work you show. So anyway, so there's three big rules here: power rule, product rule, quotient rule. But here's the deal, and we've talked about trig rules already. We'll do a little more trig on the back. But here's the deal. Usually there will be rules within rules. Meaning you're not going to just be given a problem that has one kind of derivative rule to be done. There's going to be multiple derivative rules all mixed into each other, okay? And the order you do them makes a difference. So like on this one, when I say what's the big picture rule, I'm saying what's the rule that everything else is sort of inside of. Okay, so some people might think, oh, well, the derivative of this would be 3x squared cosine x. Well, that's really wrong. There's a product rule here that ties everything together. So that's kind of like the big picture rule. The x cubed, power rule, the sine, trig rule, those are inside. Those are more specific. So we need to start by thinking product rule and say, okay, well, in the product rule, we would do this times the derivative of that plus that times the derivative of the other, or vice versa, right? That's one of those rules we just talked about. And then we usually want to write our final answers a little nicer. Like, this is potentially confusing, Someone's going to multiply those together, meaning the x and the 3x squared, and make it 3x to the third, which is not good. So it might be better. I mean, that's fine if you write it like that, but then right away, we usually want to put this in front. So it's very clear. Okay. So y prime equals x cubed cosine x plus 3x squared sine x. This is the way you should write your final answer for these, just to make it nice and understandable. Okay. Next problem. What's the big picture rule? Quotient rule. The Lodi-High one, because everything's inside of a big fraction. Now, inside the fraction, we got trig, we got power, we got products. We got like 4 different rules on this. So, but the quotient rule is sort of the main one that everything is tied together with. So we need to do low d high minus high d low. Now d low has a product right here, right? So x times derivative of sine is cosine x plus sine x times derivative of x is 1. Derivative of 2 is 0. All over low squared. Now you'll see I'm putting tons of parentheses, which I always do on these because it's so easy to lose track of something, not distribute something correctly. I mean, usually you're going to have multiple term stuff. And so you got to, I'm just, especially with quotient rule, because of subtraction, because of the power of 2. So now let's see if we can clean this up. let's see, we should probably distribute this. This is going to be x sine x cosine x plus 2 cosine x minus x sine x cosine x minus sine squared x. Now the bottom I'd probably just leave factored. Now the top I'm blowing everything up because I might be able to combine like terms. I might be able to refactor it afterwards. And so let's see. Hey, x sine x cosine x minus x sine x cosine x. So we're able to clean it up a little bit. And this would probably be, one of the better final answers. Okay. All right. I got another one right here. We got a couple options here. We could do product rule. We could do product rule. So let's try that. That would be f prime of x. First one times the derivative of the second one plus the second one times the derivative of the first one. And then distribute 2x squared plus 2 plus 4x squared plus 6x. Combine like terms, write it nicely. 6x squared plus 6x plus 2. So that's one option. The other option is we could just FOIL this first, and then it would be a pretty simple derivative because it'd just be all power rule. So we could have done this in previous units before learning the product rule. If we say, oh, it's 2x cubed plus 3x squared plus 2x plus 3. So if you take the derivative of that, well, that's pretty easy. That's 6x squared plus 6x plus 2. Hey, same answer. So, I mean, that's an option, but the product rule is going to be handy. Find A and B if the tangent line drawn to this curve has a slope of 14. So, tangent lines. There's things about tangent. If you have a tangent line, there's two things that, they share a point on the line, share a point with the line, right? And they share the slope at that point. So there's two things. So if you have two unknowns, that should help you. So one, this xy pair, well, find A and B if the tangent line drawn. Okay, so this is a point. So we could plug that in. 16 equals a 2 squared plus b times 2. So 16 equals 4a plus 2b. So that's one relationship for A and B, is that they share the point. And then the slope would be y prime equals 2ax. No product rule there. A is just a number plus b. And so then when you plug 2 in, you should get 14, right? So that gives you 4a plus b equals 14. So that's your other relationship between A and B. So this is a system of equations. You could use substitution. You could use elimination. Elimination will work really nicely in this one. You could subtract 4a minus 2b minus 16, and then the a's get eliminated. You get negative b equals negative 2, and you get b equals 2. And then you substitute this back into either of those equations to find a. 4a plus 2 equals 14. 4a equals 12. A equals 3. So system of equations, but using the fact that they share a point to get one relationship and they share a slope to get the other one. You're going to have something like that on homework problems. So that would be like the end of day one notes. And this is all you need for the day one assignment, which is listed on the back. And these rules, you're going to want to do all these homework problems. I'm giving you guys a fair amount of problems because you really got to get practice with these. There's, you just got to get good at the details of it. Now, we did sort of a proof, not really a proof to find the derivative of sine before, and I'll go ahead. It's more of a visual, way of trying to figure it out. So we said, oh well, let's look at a sine curve. And then we said, well, let's try and graph the derivative of that, And we're getting pretty good at graphing derivatives now after the last chapter test, right? It should probably be a smooth graph. Slope is 0 there, so it's going to be 0 here. Slope is 0 here. So 0 here. Slope is about 1 there. Slope is about -1 there. Slope is about +1 there. If we connect it with a smooth graph, we get a rough sketch of the derivative graph, which looks like cosine. So the derivative sine equals cosine. Nice. Now the derivative cosine, you might think, oh, well, that's just going to be sine. Not quite. We could kind of do the same thing and say, okay, well, slope there is about 0, slope there is about 0, slope there is about 0, slope here's like -1, slope here's like +1, and it's like a sine curve, but upside down. So derivative cosine is sine, but negative sine because it's flipped upside down. Anyways, those aren't super technical proofs, but just another interesting way. So the derivative sine is cosine. Derivative cosine is negative sine. Now let's see if we can figure out tangent, the derivative tangent. And I think we did this one actually in the warm-up, in the last chapter. We said, okay, well, that's going to be derivative sine over cosine, right? And we said, oh, we should use quotient rule. I showed it to you guys briefly last unit, but I showed it to you more official on the front of these notes. So it's going to be low d high minus high, which is sine x, times root d low, which would be negative sine x, all over low squared. And then that's going to give you cosine squared plus sine squared over cosine squared. And cosine squared plus sine squared is 1. And so then the derivative tangent x equals secant squared. Derivative tangent equals secant squared. Now, why don't you guys try one real quick? Why don't you guys try secant? See if you could figure out secant, just as practice. Hint, right away, I would change it to sine and cosine. Okay? So we could do quotient rule. Low d high. What's the derivative of 1? 0. Low d high minus high d low all over low squared. That term drops out. So we get sine x over cosine squared x. Now, maybe we could write this in a little more friendly version. What if we did 1 over cosine times sine over cosine? That's the same thing, right? And then what is 1 over cosine? Well, that's secant. What's sine over cosine? Tangent. The derivative of secant is secant tan. Derivative secant is secant tan. Now, I'm not going to do the others, but there's some patterns that you want to learn here. You want to do sine and cosine together, right? If tangent is secant squared, what would you think cosecant would be? Cosecant squared. But negative. You might notice that you're going to notice this, that anything with a co is going to have a negative answer for sure. Okay? So, which ones are negative? My trick is co, anything with a co, derivative, has a negative. Okay? Cosine, cosecant. By the way, we don't usually see the CO necessarily all the way. Cotangent, because we abbreviate these things. But anything with a co is going to have a negative. Now, if tangent, I messed up. If tangent secant squared, cotangent is cosecant squared, negative. If secant is secant tan, then cosecant is cosecant cotan, right? So they have these patterns where if you know one, you can kind of extend it to the other one. So I kind of remember them in pairs. That makes it a little easier. And then all the codes have negative answers. Okay, here's a couple more examples. I'm just using some trig. Find the 30th derivative of y equals sine x. Well, that's going to take forever. If I give you something like that, you should probably think in the future now, there's probably a pattern, and I shouldn't have to do them all. But let's see if we can find the pattern. Makes it easier if you start doing them. So I'm going to say, all right, well, the original function was sine. The first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. The fourth derivative is positive sine. And then if we keep going, the fifth derivative is cosine. And we're repeating ourselves, right? Once we get here, we're back up to there. So really, there's this group of derivatives, and then they're going to keep repeating themselves, right? Forever. Now, I'm going to consider this the zeroth derivative, okay? Because what we want to do now is take out all the even groups of 4, because they each start you back at the beginning and just figure out what's left afterwards. So we're going to do a little division here. 30 derivatives, take all the groups of 4 out. That would be 7 of them. And there would be 2 left. This is the remainder. And this is really what's important in this pattern. Because remainder of 2 means it's going to be the same as the second derivative. The 30th derivative is the same as the second derivative. The 30th derivative, by the way we write these big derivatives, we put them in these superscript parentheses. Y prime acts like that with that little 30. It means the 30th derivative is going to be the same as the second derivative. Okay. Now, if you got a remainder of 0, it'd be the same as the original problem. So I like to put a little 0 in parentheses there to kind of be like, that's the 0th derivative. Find all the points on 0 to 2 pi where this graph has a horizontal tangent. Now, we've been doing this before. Horizontal tangent means that the slope equals 0, right? So we need the derivative. Y prime 2 cosine x equals 0. So now we get to solve a little trig equation that we've been doing a bit of this year. Cosine equals 0 at pi over 2 plus pi k. So x equals pi over 2 and 3 pi over 2. Those are the answers. Now these are the x coordinates, which might be good enough. It said points. So if they said x coordinates, I would just do that. So maybe we should find the y coordinates also. So we could do that. Plug pi in here. 2 sine of pi over 2 plus 1. Sine of pi over 2 is 1. So that's going to be 3. So one of the points is pi over 2, 3. And then y, 3 pi over 2. That's going to be negative 1. So that's going to equal negative 1. So the other point is 3 pi over 2, negative 1. So these are the 2 points. Okay? So your assignments for day 1 and day 2 are from the same pages in your book. And day one, we do 1 to 27 odd, 39, 45 odd, 58 to 60 odd. Check all the odds in the back of your book as you're going just to see if you're doing good. And then we'll check that assignment. We'll fix the problems. We'll figure out the ones you got stuck on. And then you'll try the second assignment. But wait till you like really figure out the first one before you start on the second one. Okay? All right, we got to get you have to get good practice at this tedious stuff, okay? So you guys are gonna love this because it's really about a lot of little tiny rules and details that we are gonna memorize and just become good at executing.